Let us start with today's class. And just let me to come closer to the microphone. Okay. Today what we are going to look at is a very typical thing in digital design, and many gate problems and other things in the gate exam are also dependent on this part of the chapter. So let's look at that. So this is nothing but excitation tables, characteristics equation, transition table of the flip-flop. So these are three very unique things which we need to analyze counters. So you need to understand why we are doing this. We are doing this because we want to look at counters, and counters will depend on all this. That is the excitation table, the characteristics equation, and the transition table of the flip-flop. So what all these things are, that is what we will see, and how to derive. So over a period of time, these transition tables will sink in you, but in case you forget how to derive them, is going to be the part of today's discussion. So let's go ahead and see. So first is characteristic table and equation of the flip-flop. So you must have heard about truth table. So the closest that you have come, the table word that is associated in digital design is generally with truth table. So gates have a truth table. Gates will have truth table. But flip-flops will have truth table as well as characteristic table. So it has both. So we have seen the truth table part of the gate, but we have not yet seen the characteristic table of the gate. And once we look at the characteristics table, we can look at the characteristics equation of the flip-flop. Now, what this characteristics equation is and all those things we will see now. So first thing, in a flip-flop, the relationship between input and output are not very straightforward. The relationship between input and output are not very straightforward. That means it is difficult to write Q is equal to something in terms of S and R or J and K. For example, we used to write in gates Y is equal to A dot B. So now what we want is we want to write the output in terms of SR and JK, something like that. So we want that. Now the output of the flip-flop doesn't just depend on the current output, but it also depends on the past output. That means if I want to know that initially if my output is Qn along with some input J, K, SR or T or D, whatever, then what is going to be my Qn plus 1? That is what is going to be my next step. So you have seen that flip-flop has got Q and Q bar outputs, and many times that Q and Q bar is fed back as input, and so the past output is also going to be very important in determining the next state output. So here we have Qn and Qn plus 1. So as I am showing you these points, please write it down. The second thing is, hence, to analyze the logic function of a sequential circuit. So for a combinational circuit can be analyzed by using any of such functions. Y is equal to A plus B bar dot C, something like this. So you can always analyze that. But for a sequential circuit also we want to have something similar because it is easier to implement such kind of functions using basic logic gates. Hence, to analyze the logic function, of a sequential circuit, it is very important to know the characteristics of each flip-flop in detail. So we want to find out now characteristics of each flip-flop in detail. The characteristics table defines. Now let us look at the first thing. The characteristic table defines the next state output of the flip-flop. Next state means Qn plus 1 of a flip-flop as a function of the present state output and inputs. Of the present state output and input. So very important. If it's a JK flip-flop, then Qn plus 1 will depend on JK and current output. Qn plus 1 will depend on JK and current output. So what does the characteristic table define? The characteristic table defines the next state output. It defines Qn plus 1 of a flip-flop as a function of the present state output and inputs. As a function of present state input is Jk, for example, of a Jk flip-flop, and the output is Qn. Qn plus 1 is named as next state output and Qn is named as present state output. So many times the shortcut words are Ns and Ps. Ns means next state and Ps means present state. Clock is not used to describe. So please remember, clock is also like an input to the flip-flop, but clock is not used to describe the characteristic table. But does it mean that it is not there? Yes, it is always there, but the table is derived considering clock pulse is always active. So though clock is not used, we know that if clock is not there, then the flip-flop will not trigger at all. So clock is assumed to be there and it is considered to be active at all times. The characteristic equation. So here we spoke about characteristic table. So characteristic table defines a relationship between Qn plus 1 and Jk and Qn. The characteristic equation for each flip-flop is derived using K-map simplification method. So again, can you see K-map has come into picture? So K-map is again very important. The characteristic equation for each flip-flop is derived using K-map simplification. So first we have truth table of flip-flop. Then we create characteristic table of the flip-flop. Then we create characteristic equation. And then we create something called as transition table, or it is also called as excitation table. Transition table or excitation table. So please write this 6 points down. This is enough for our today's discussion. So once you are done, please put done in the chat box. please put done in the chat box. Karthik, can you hear me?
Yes, sir, I can hear.
Okay, and screen is visible, right?
Yes, sir, screen is visible.
So you all are writing because I have not received any comments.
Yes, sir, we are not done yet.
Okay. So once you are done, just write done in the chat box. So those who have joined a little bit late, this is the first slide. So you can either take a screenshot of this or you can write it down. It's up to you. Anyways, I'm going to share this later on, but for the sake of it. So characteristic table and characteristic equation are the two keywords that we have to focus on. So we have truth table, then we have characteristic table, then we go to characteristic equation, and then we try to make excitation table. So two, three different things are required for a flip flop. Okay, so let's go ahead with the characteristic table and equations of different flip flops. So for us, different means SR, JK, T, and D. Only four flip flops: SR, JK, T, and D flip flop. So let's do that. So first is characteristics table and equation of SR flip flop. Characteristic table and equation of SR flip flop. So first is truth table. So please recall the truth table. So you will write now everything with me because this is going to be kind of a flow and you should be able to understand that. So first everybody will write down the truth table of SR flip flop. So like we know S is 0, R is 0, we have a no change condition, and when 0 1 we have a reset, and 1 0 is set, and the last one is the forbidden condition. We don't operate SR in 1 1. So generally we don't care what this is. Okay. So just write this. Okay, good. I can see everybody has completed. Let's now you copy the truth table, that is TP. You have already done this, but just there in front of you. Now, characteristic table gives me Qn and Qn plus 1. Characteristic table will give me Qn and Qn plus 1. So, actually, Qn plus 1 should be a function of Qn S and R. Qn plus 1 should be a function of Qn, S and R. So from the truth table, you can see S and R can take four different values. S and R can take 0, 0, 0, 1, 1, 0 and 1, 1. And Qn by itself can take values of 0 or 1. That means when S and R is 0, 0, Qn can be 0 or 1. When SR is 0, 1, Qn can be again 0 or 1. When SR is 1, 0, Qn can again be 0 or 1. The initial state can be anything, either 0 or 1. So what we do is everything in SR truth table can have two possibilities of Qn, that is 0 and 1. So that is why we go to a next table, that is characteristic table. So you can see that for these are my present state inputs, these are my present state outputs, and these are my next state outputs. So basically my next state output Qn plus 1 should be a function of Qn, S and R, should be a function of Qn, S and R. Qn bar is okay, we are just writing this as a formality, and Qn plus 1 bar is also, we are writing it as just a formality. So here we are having SR, Qn and Qn plus 1. Now it is important to understand that what we are trying to do is establish relationship between Qn plus 1, Qn, S and R. So you can see from in the characteristic table, S and R can take four different values: 0, 0, 0, 1, 1, 0 and 1, 1. However, for each value of S and R, Qn can take value of either 0 or 1. Qn can take value of either 0 or 1. That is why we get here 8 different combinations. So actually, now my Qn plus 1 will depend on S, R and Qn, where Qn can be 0 or 1 for any of these combinations. But once you clock this flip-flop, but once you clock the SR flip-flop, for 0, 0, we have no change condition. No change means whatever the output is, it will remain the same. That is why when S and R is 0, 0, if Qn is 0, my output next state is going to be 0, and if Qn is 1, my next state is going to be 1. If you look at the next condition of SNR, that is 0, 1, here we have a reset. That means whatever may be the value of 0 and whatever may be the value of the current state output, that is the present state output, my next state output will always be 0, 0 only. My next state output will always be 0. 1, 0 is set condition. That means whatever may be my present state output, 0 or 1, once I clock the flip-flop, my next state output will be just 1, 1. And here 0 and 1, last condition, that is we have just writing here forbidden. Next state is going to be kind of forbidden. So we would not like to operate in this state. So basically I will write this forbidden as don't care. I will write forbidden as don't care. So you can see I wrote the truth table. I wrote the characteristic table from the truth table only. But now I included two possibilities of Qn, that is 0 and 1. And based on the truth table for 0, 0, Qn was no change. No change means if Qn is 0, output will be 0. If Qn is 1, output will be 1. 0, 1, SR is 0, 1, then Qn will, if whatever may be the value of Qn, the next state will be reset. So you can see that this is going to be reset output, and 1, 0 is set output. So here we can see whatever may be the present state output, the next state is going to be 1, 1. And in the last state we have forbidden. So I have just written the same thing here, forbidden. Whatever may be the present state output, the next state is going to be the forbidden output. So any doubts in this, please ask and copy this truth table as well as characteristic table. So once you are done with this truth table and characteristic table, write TT and CT done in the chat box. TT and CT done in the chat box. Okay, great. But I'll wait for 1 minute just to complete this thing. Okay. So in my next slide, the characteristic table will still be there. So let us go to the next slide. So I am just noting it down here that Qn is present state output, and Qn plus 1, if this is present, next state is going to be n plus 1. Now, how to do K-map simplification? So you can see the characteristic table now. Okay. So my inputs are going to be S, R, and Qn. My inputs are going to be S, R, and Qn. So you can observe in that for you can observe in that same table for which conditions Qn plus 1 is 1. Can you tell me for which values of S, R, and Qn plus 1 is 1? So for 1 it is 1, then for 2 it is 0, for 3 also it is 0, then for 4 it is going to be 1, for 5 also it is going to be 1, and 7 and 6 they are forbidden, but instead of forbidden we will write don't care. We will write don't care. So this is the truth, this is the K map that you will get. So now can you tell me Qn plus 1 in terms of SR? So we have here one quad and here we have one pair. So this pair quad will give me S because here S is 1, and here this is going to be R bar and Qn. R bar and Qn because it's a vertical pair. So what I will get? So Qn plus 1 is going to be S plus R bar Qn. Qn plus 1 is S plus R bar Qn. Qn plus 1 is S plus R bar Qn. This is called as the characteristic equation. equation of the which flip flop are we saying? SR flip flop. This is the characteristic equation of the SR flip flop. So please write this. Once you have done this, write K map done. So see the characteristic table to fill this K map. Look at the column of Qn plus 1. Qn plus 1. So you can see, I'll just go back if you want. Here Qn plus 1 is 1 in this place, then this and this. And there are two don't cares. So in all there are 3 ones and 2 don't cares. So 3 ones and 2 don't cares. You can very well identify that. 3 ones and 2 don't cares. So this one is for 1, 2, 3 is 0, 0, 4, 5 is 1, 1, and 7 and 6 are don't cares. So write the characteristic table and characteristic equation. Okay, good. So I can see many have. Shubham has given the answer first. Asmita 145 is correct, but don't cares also have to be considered. Okay, Divya Jain, how there
Okay,
is
sir.
present state output S equal to 1 and R equal to 1. Maybe I didn't get that question. Can you please elaborate on that? Okay, so let's go ahead. Now my characteristic table is there in front of us. Now let's look at something called as excitation table. So how many tables does a flip flop have? First is we started with truth table. Then we went to what? Characteristic table. And now we are going to the excitation table. So if you look at the characteristic table the other way around, that is if you want now to write S and R in terms of Qn and Qn plus 1, then that table is called as excitation table. If you want to write inputs in terms of outputs, that table is going to be called as excitation table. So now I will suggest you to look at only this column, the columns which I have picked, Qn and Qn plus 1. So look at only this much. Look at only these two columns. Okay. Now, the excitation table for this flip-flop is somewhat like this. The excitation table for this flip-flop is somewhat like this. Now, how did we do this? So here, these are my outputs and inputs I am trying to write in terms of outputs. Inputs I am trying to write in terms of outputs. So you can see here Qn is 0, 0. The Qn is 0, 0 at two places. You can see here Qn is 0, 0 at two places. Qn and Qn plus 1 is 0, 0 at two places. Now, if you look at these two terms, carefully, you can see even if Qn and Qn plus 1 are 0, 0, S is always 0. S is always 0. But R can be either 0 or 1. But R can be either 0 or 1. So which condition can accommodate both the values 0 and 1? So it is my don't care condition. Now, if Qn and Qn plus 1 is 0, 1. So 0, 1, let us identify where is 0, 1. Yes, so we have 0, 1 here, and that's it. So we have just 1, 0, 1. If you look at 0, 1 condition, then we have S and R as 1, 0. S and R as 1, 0. So I write here 1 and 0. Next is 1, 0. So where is 1, 0? Yes, you can see here 1 and 0. Anywhere else you can't see that. So 1, 0 means S and R is going to be 0 and 1. So I write here S and R is 0, 1. And 1 and 1, 1 and 1, we have in two places again. So here we have Qn and Qn plus 1 as 1, 1. So just don't see this for some time. And here also Qn and Qn plus 1 are 1 and 1. So now if you look at this S and R, and if you look at S and R here, so you can see R is always 0, R is always 0, but S can be either 0 or 1. That is why I wrote here don't. And you really cannot say what is 0 and forbidden. So we discard this condition. We discard this condition. What is forbidden, we don't know. So this is how we define the excitation table of the flip-flop from the characteristic table of the flip-flop. Any doubts in this, please ask me, unmute and ask. And note down the excitation table. No need to write the characteristic table again. But I just now told you how to generate the excitation table from the characteristic table. Yes, any doubts? Please unmute and ask. Okay, if excitation table is done, just write ET done in the chat box, please. Sir, in the present state, how are we getting outputs for forbidden condition? In the present state, how are we getting outputs for forbidden condition? Divya, see, whenever we start a particular circuit, either the circuit will be in set or reset. Either the circuit will be set or reset. That means all outputs will be initially 0 or all outputs will be initially 1. But the moment you clock, the moment you give S and R as 1, 1, when the system is initially reset, you are not giving any input. So there is no question of forbidden condition. But the moment you give 1, 1, it will go into a race around condition. So that output is forbidden. The present state can have any output, that is either 0 or 1, because initially the system will be either set or reset. I hope I have answered your question, Vijay. We are talking about the present state. We are not talking about the next state. Next state can always be 4 digit. Okay, so we will do this for 2, 3 flip flops. Then you will get the hang of this. So this is the final thing in excitation table. Again, I have just highlighted that Qn and Qn plus 1 are the present and the next state outputs. Okay, let's look at the next thing, characteristic table and equation of D flip flop. Characteristic table and equation of D flip flop. So first look at the truth table of D flip flop. So please note that D flip flop is a set reset flip flop. D flip flop is a set reset flip flop. So when you give 0, the output is reset, and when you give 1, the output is set. So because D flip flop operates only on the middle two conditions of SR flip flop, that is 0, 1 or 1, 0. So this is the truth table, and then the characteristic table would be for every condition of D, there could be two conditions of Qn. Qn can be either 0 or 1. So when D is 0, Qn can be either 0 or 1, and when D is 1, Qn can be again either 0 or 1. So please note down the characteristic table. And now we want to write Qn plus 1 in terms of D and Qn. Qn plus 1 in terms of D and Qn. So previously we wrote Qn plus 1 in terms of SR and Qn. That is why we required a 3-variable K-map. That is, the 3-variable K-map will be with 8 cells. Now here Qn plus 1 is only in terms of D and Qn. That is, it is dependent only on 2 variables. That is why we will require a 2-variable K-map which will have 4 cells. So please note, if this is 0, 1, 2 and 3, so 2 and 3 are going to be 1. 2 and 3 are going to be 1. So now these are my inputs, and this is going to be the output. Okay, so if characteristic table is copied, please write CP done. Yash has written CP don't. What exactly do you want me to go to the next slide or no? Yash. So instead of writing present state, next state, you can write here PSOP, and here you can write NSO, present state and next state. The shortcut. So again, I am repeating We are trying to define the next state based on present state input and present state output. Okay. So can you go ahead and make the K map? Can you go ahead and make the K map? Okay, great. Can see many people being done. Let's see the K map. Now it will be a two variable K map. And I told you that only 2 and 3 are 1. So here we will have the K map which is 1 and 1, and that will give me just D. So Qn plus 1 is D. So this is the characteristic equation of D flip flop. Characteristic equation of D flip flop. So if K map is done, just write K map done. It's a very simple K map. Okay. So let's go ahead and try to see the excitation table. So you can see in the excitation table we have only 4 combinations of Qn and Qn plus 1. So we have Qn, then we have Qn plus 1, and we have the input. So Qn is 0, 0, 0, 1, 1, 0, and 1, 1. So for 0, 0, D is 0. For 0, 1, where is 0, 1? Here D is 1. Then for 1, 0, where is 1, 0 here? What is D? Again 0. And for 1, 1, D is 1. So we have 0, 1, 0, 1. So you can see that the excitation table is 0, 1, 0. So you can see that one observation here in D flip flop, that the next state is equal to the present state input. The next state output is equal to the current state input. And that is why it is called as a delay flip flop. So the output is delayed by the amount of the clock. The output is delayed by the amount of clock period. So if the clock period is 1 second, that is 1 hertz. If the frequency is 1 hertz, then it is going to be 1 second. Okay, write down the excitation table, and if excitation table is done, you can write ET done. We can write ET done in the chat box, please. Okay, so let's go to the next one, that is characteristic table equation and excitation table of JK flip flop. So first you write down the truth table. Now in JK, we don't write here forbidden. because in JK the outputs are defined. It is Q and Q bar. So write the truth table. So JK takes care of the race around condition. So please start making the characteristic table for this. Please start making the characteristic table. So the characteristic table will be like this. So we have two combinations of JK 01, 10 and 11. For each combination of JK, we can have input as 0101, and the first condition for JK is no change. That is why this will be the same as this one. So Qn plus 1 will be equal to Qn. Then we have reset. So whatever may be the present state output, the next state output will be 00. Then here you have 11, and here you can see if the present state output is 01, the next state output will be 10. So just to highlight here, this first two will be no change, this will be reset, this will be set, and this will be toggle. That means if it is 0, it will toggle to 1. If it is 1, it will toggle to 0. That is what this Q bar indicates. So once you copy the truth table and characteristic table, write AP and CP done. So now what is different as compared to SR? That forbidden state has gone. Now we are having a toggle condition there. Okay, those who have finished with the characteristic table, they can go for the K-map. So you will require a 3-variable K-map. So the inputs to the K-map will be J, K and Qn, and the output will be Qn plus 1. So these are your inputs and these are your outputs. Okay, Ashlesha, go ahead with the K-map. Okay, I'm going to the next thing, that is K-map simplification. So you can see in which places the output was 1. So for 1 the output is 1, then 2, 3 the output is 0, then again 4 and 5 the output is 1, And for 6, the kn plus 1 is 1, 7 is 0. So this is how the output is. Please note there are no don't cares because there are no forbidden conditions. So can you tell me the characteristic equation by solving this K-map? Can you post the characteristic equation? Okay, Omkar has posted it. JQN bar plus KQN. Let us see. This is one pair. This is another pair. So JQN bar is correct, Omkar, and K bar QN is also correct. Yes, absolutely correct, Omkar. Very good. So the characteristic equation will be Qn plus 1 is equal to. So this is the characteristic equation. Good. Okay, Divya, KQN bar. It's not KQN bar. Divya, it is K bar QN. Asmita, your answer is also right. Divya, just check the KMAP. They have written slightly reverse. Yes, Suman's answer is also correct. Okay, so let's go to the excitation table now. So the excitation table is like this. Now let us see how. So let us look at the first condition, that is 0 0. So where can I see 0 0? Here 0 0 and 0 0. Where else can I see? Here 0 0 and 0 0. So for this I have jk as 0 0, and for the other condition I have jk as 0 1, which means j is always 0, but k can be anything. It can be either 0 or 1. That is why I have written here a don't care condition. Next one is Qn and Qn plus 1 is 0 1. What if they are 0 1? So let's identify that. 0 1 is here, and here also 0 1. So for these two conditions, let us see what is j and k. J as k is 1 0 and 1 1, which means again j is 1 always, and k can take any value, that is 0 and 1. That is why again it's going to be a don't care. Okay, next is 1 0. Next is here 1 0. So let's see where is 1 0. Here we have 1 0, and here also we have 1 0. So let's highlight those cells here. See 0 1. Okay, so now j can take any value 0 or 1, and k is 1. So that is why j is don't care, k is 1. And finally we have 1 1. So let's see 1 1. Now only two are left. This is 1 and 1, 1 and 1. So what are the outputs? Jk can be 0, 0 or Jk can be 1, 0. So J can be 1 or 0, so don't care, and K is 0. So I think we have addressed all the cases, and that's how we made the excitation table. So please write the excitation table. If you have finished drawing the excitation table, write ET done. Okay, it was autocorrect. Okay, but you have got that answer, na? Divya? Yeah, okay, correct. So if excitation table is done, let's write excitation table is done in the chat box, please. Quickly done, okay. Ashlesha, what about others? Please look at how I am backtracking. So that this backtracking is also very important. Okay. Now you all will do the truth table, the correct truth table I will show you for the T flip flop. Truth table I will show you for the T flip flop. Now based on this, you will generate the characteristic table, the characteristic equation, and the excitation table of the T flip flop. Come on, do it. I will give you 5 minutes to do it. Okay, Tanvi, Gaurav, Suman, Kritik, Apurva, start with the T flip flop. Deepak, Asmita, Amit, go ahead and complete the characteristic table of the T flip flop. Characteristic table, then K map. So K map you are doing for characteristic equation, and then finally the excitation table. So please preserve the notes and everything of this subject, because this subject you will get around 8 questions in the GATE exam also. So, and these things are very logical here. I think it is easier to attempt it. Okay, so I am showing you the characteristic table. So T flip flop runs. So first condition is no change, and the second condition is toggle. Toggle means 0 1 is 0 1 only here, and if it is 0 1, this will become 1 0. That is toggle. So now you will write Qn plus 1. This is your output in terms of P and Qn. This here. So you will use a two variable Kmap. So what is the characteristic equation? By looking at Qn plus 1 only, you should be able to tell actually. So I am going to the next one, that is Kmap. So you can see here in the Kmap which all things will be 1. So that this is 0, 1, 2, 3. You can see here that Qn plus 1 is 1 for 1 and 2. So we have Kmap, and 1 and 2 is 1. 1 and 2 is 1. So that will give me a Kmap which is this way. Give me a Kmap which is going to be this way. And I have one isolated cell, and then we have another isolated cell, and both these
So can
isolated
you
cells. Sorry,
so can you please go to the previous slide? I think you are going very fast because I'm not able to write. Also, I have not completed K map simplification and excitation table of D flip flop.
who's this actually?
Sorry,
Who's this speaking? I can't hear.
Vishwas.
Vishwas. Okay.
Yes, sir.
Okay. So you stop me. I'll wait. No problem.
Okay. Thank you, sir.
Yeah. So others, please go ahead with the excitation table. Vishwas, instead of copying it down, I would like you to solve it on your own. So try to solve on your own, and if you face a problem there, then you ask me. Don't rely much on the slide. Where you are facing the problem, Vishwas?
Sorry, sir. I don't get the
Are
question.
you facing any problem in understanding?
No.
Okay. So writing speed
Yes.
is the problem.
Yes, sir.
Okay.
This is
Okay. This PPT is done.
yes, sir.
Okay. I'll go to the PPT of the K map. So you don't write the first K map, Vishwas. Write only the second one. The first one is only for your explanation. So write only the second one. Okay.
Okay, sir.
Don't write
Yes, sir.
everything what I have written because I am writing with respect to explanation. You write it with respect to your understanding. So just write the second K map. All of you, not just Vishwas. All of you should write only the second K map, not the first one. First one is for me to scribble something on. Okay, so these are my two terms. Yes, let me check P XOR QN. That is right, Shubham. So you can just use one XOR gate. So this is the characteristic equation of the T flip flop, which is also P XOR QN, as Shubham has rightly observed it. Good. Okay, Asmita also. Yeah. So should we go to the next one, excitation table? Yes. Go to the excitation table. So I think you can map this excitation table now. You need to look at this and this. So 0, 0 is 0, 0, 1 is 1, 1, 0 is again 1, and 1, 1 is 0. So this is the excitation table of the T flip flop. Okay. So don't write the characteristic table again. Okay. Just write the excitation table. So you will write the truth table once, then the characteristic table once, then you will solve the K-map and then write the excitation table. Please note, to write the excitation table, you don't have to do characteristic equation. You can go to excitation table without even doing or calculating characteristic equation. Okay, Gaurav, this is done. Okay, so let's do the summary of all the excitation tables which we will be requiring for our next part. So now we have derived the characteristic table for every flip-flop. We have derived the characteristic equation for every flip-flop. Then we have also derived the excitation table of all the flip-flops. Now these characteristic table, characteristic equations and excitation tables will be our tools to analyze counters and to convert one flip-flop into another. So many times you may have a JK flip-flop, but you may not have T and D flip-flops. Or you may have T flip-flop, but you may not have JK and D flip-flops. So is there a way to do the conversions between the flip-flops? That is the question. And that is why we have to go to the next thing, that is see the conversions between the flip-flops. So let me go to the summary of the excitation tables. So this is the summary. So please note it down. And this is only what we will see when we want to do the conversions. We will not look at the characteristic table. We will not look at characteristic equation, nothing. We will look only at the excitation table when it comes to higher analysis. So that is why this is the summary of everything. So please write it down. So these are your outputs actually, and these are the inputs of SR. This is the input of D. This is the inputs of JK, and this is the input of P. So this is the SR flip-flop excitation table. This is the D flip-flop. This is the JK flip-flop, and this is the T flip-flop. So let us take a break of 10 minutes and resume back after 10 minutes. So we will try to take a 10 minutes break after every 1 hour. In the meantime, we can just copy this excitation table down. Those who have done it, we can just take a 5 minutes, 10 minutes break. So we'll resume back at 11:25.
Hello, sir. Hello,
Yes.
sir. Why the characteristic table required?
It is used to convert one flip flop to another flip flop, and it is also used to design a specific type of counter. So
O-
the real use of this is we are yet to see that. So now we will see that only.
okay, sir.
So just try to keep these characteristic excitation tables at the back of your mind.
Okay, sir.
Okay, so it's 11:25. So let us look at uh, our next part of this chapter, that is flip-flop conversions. So how to convert one flip-flop into another. So what we are going to see is how to convert one flip-flop into another. So like I said that majorly we have SR, then we have JK, then we have D and T flip-flop. SR, JK, D and T flip-flop. So when we are saying that we want to implement SR flip-flop, so how to implement SR using JK, D and T, that we will see. When we say JK, how we can implement JK using SR, D and T. When it comes to D, it would be how to implement D using again SR, JK and T. And when it comes to T flip-flop, so you can see that how to implement T using SR, JK and D. So in all, you can see that SR can be implemented in three ways, JK can be implemented in three ways, D also can be implemented in three ways, and T also can be implemented in three ways. So all these methods we should know. So precisely there are going to be 12 implementations, and all these 12 we will see today, or rather at least try to see one of each, how to do this. Okay, so that is for the thing for today. So let me go to the slide now. Okay, so like I said, I have just added this slide of excitation table summary of all the flip-flops, because that is the fundamental of conversion of one flip-flop to another flip-flop. So let's see the procedure. Qn is present state, Qn plus 1 is next state, output. Realization of one flip-flop using another flip-flop. So in the exam, this is a very typical question which is asked for 10 marks, and you may have to convert one or two flip-flops into using another two flip-flops. So please understand the procedure very carefully. So first we'll write the procedure down. First, write excitation table, write excitation table of a flip-flop that is used to realize the other one. That is used to realize the other one. Write the input conditions of the flip-flop that is to be realized from the excitation table. So write the excitation table of a flip-flop that is used to realize and to be realized. These are two different things. So if we say SR using T, then the excitation table of a flip-flop that is used to realize another one. What will we have here? So the excitation table of a flip-flop that is used to realize another one. So here we will write T flip-flop excitation and write the input conditions of a flip-flop that is to be realized from the excitation table. So here we will write to be realized is SR using what? Just an example. There can be many such examples. So this is the step 2. Step 3. Simplify and obtain the characteristic equation for the input. So characteristic equation for the input of the flip-flop. Characteristic equation for the input of the flip-flop. So what does this mean? What does this mean? Let us say I have a SR flip-flop. I have a SR flip-flop, SR, Q and Q bar. Let's say I have this. Now I want to implement a T flip-flop using SR. I want to implement a T flip-flop using SR. So actually speaking, this SR will be inside a black box. I will give T here. This is going to be my T. And it will also give a clock here. And this will have some outputs, Q and Q bar. SR is a part of it. So now to convert SR to T flip-flop, I need to put some hardware around SR. So hardware plus the SR flip-flop is going to be the T flip-flop. Now to design this hardware, we require excitation tables. We require excitation table. So that hardware will be using some basic logic gates only. It will not be very difficult. So input of the flip-flop that is to be realized in terms of present state Qn using K-map. Then input of the flip-flop is used to realize it. And the fourth is draw a logic diagram of the flip-flop by realizing the simplified characteristic expression obtained in step 3. That is here, because here you are doing the characteristic equation using a flip-flop, very important, and logic gates. Using a flip-flop and logic gates. So that's what I told you. Right now here, if you see, to implement a flip-flop, you require another flip-flop and some hardware. So this hardware will come from excitation table using the K-map logics, and you will require a flip-flop to implement any other flip-flop. So please write these points down quickly. Once you have written these points down, write them in the chat box. Okay, please write this little bit quickly. That's it. These are only the 4 points which we have to use while making the flip flop. So I don't want to give you too much of theory. I just have one slide of some sentences and some procedures, and others will be completely problems. So I think Hemant asked me a question, what is the use of those excitation tables? So very soon we will see those excitation tables. So this point is also important. They're very critical points. Input of the flip flop is used to realize. Input of the flip flop is used to realize the characteristic equation. Anushka, Karthik, are we done with this or should I wait for another couple of minutes? Okay, I can see people writing done, but still I'll just wait for another 1 or 2 minutes. Please stop me if I'm going a bit fast, but please try and understand that we have some time restrictions. So, in case you are not able to write something, you can do it later on because everything is on record. So, you can just go back to it and write. So, no need to worry about if you miss some theory. But yes, do not compromise on the understanding part. If you are not understanding, please stop me there and there. I'll redo the whole thing again. Okay. Okay. So let's go ahead. So right then, first realization of SR flip flop using D. SR flip flop using D. So we have picked a flip flop that is SR, and now we will implement it using D. Then we will implement it using T. Then we will implement it using J. Okay. So first, look at the structure of this table. Look at the structure of this table. What we have to design is a SR flip flop, and using what? Using a D flip flop. So what I write is I write the SR transition table. So this is my SR transition table. This is my SR transition table, and this is my transition table of the flip flop to be used. Transition table of the flip flop to be used, and the transition states are common to both of them. that is Qn and Qn plus 1. So S and R, whenever we write, it is in terms of Qn and Qn plus 1. And whenever we write D, it will also be in terms of Qn and Qn plus 1. So in a way, S are a function of Qn and Qn plus 1, and D is also a function of Qn and Qn plus 1. So please write this table in this way. Please write this table in this way. First input, you will write it on the left side. That is the flip-flop to be designed will be on the left hand side of the table, and the flip-flop to be used will be on the right hand side of the table. And transition states are common to both since they are excitation table entries. That is why transition states we will write in between. Okay, so now in this case, we will use our objective is to write, we want to use D flip-flop and make SR. That means we already have a D flip-flop. That means we already have a D flip-flop. So we are having a D flip-flop. Now I have to connect some hardware here in front of the D flip-flop. So I will have to write D equal to something. I want to write D equal to something. It can be anything in terms of Qn or Qn bar, whatever. And it can be in terms of anything. So basically, we want what hardware to be connected at the input of D. That is why now to find out what hardware I should connect at the input of D. So I want D in terms of S, R and Qn. I want D in terms of S, R and Qn. So these become my inputs now. S, R and Qn become my input. So here you can see R can take two values 0 and 1, and here S can take two values 0 and 1. So actually the first condition here would be for S, R and Qn, the first condition would be 0, 0, 0. The second condition would be 0, 1, 0. Then, so we have two conditions in this first one. Then we have only one here because all there is no don't care in the second one. That is 1, 0, 0. In the third one also we don't have anything. That is 0, 1, 1. And in the last one again we have x 0, 1. So x can be 0, 0, 1 or 1, 0, 1. 0, 0, 1 or 1, 0, 1. So in all we have 6 entries. In all we have 6 combinations. That means 2 are missing. 2 are missing. So no problem. We will consider them as don't care. So let us see the excitation tables, and with respect to that we will see how to solve the K map. So if you have drawn only this table at the top, that should be enough. Please put it in the chat box whether you have drawn this table or not. So more on this, what I have written below, I will just explain it in the next slide. Okay, so let's go ahead. If you have drawn these 5 columns, now again here you may not write this. You may not write the first line of the table. Okay, you may not write one transition. It is understood that you may just write SRQN QN plus 1D, and just below that you can write these excitation tables and transition states. That is enough. I have written only for your understanding. So the excitation table is as it is at the top for both SR and D. So now we have K-map simplification. Please understand that S, R and Qn are now my inputs, and I am trying to find out what is the value of D. What is the value of D? So actually Qn plus 1 is also not required. But since transition states have Qn plus 1, we are just writing it down. Okay. So now, since there are 3 variables, the 3 variables are S, R and Qn. I will be writing D in terms of SR and Qn. So naturally I will have to write here S, R and Qn because I am trying to write D as a function of S, R and Qn. Now how to uh, fill the K-map? So let us see here. First condition is 0, x can be 0 or 1. Here x can be 0 or 1. So first condition of SR would be 0, 0 and 0. 0, 0, 0 is what? 0. And what is the value of D for that? That is 0. So we will leave it as it is. Then we have 0, 1, 0. So 0, 1, 0 is 2. And what is the value of D for that? 0. So we look for those conditions where D is 1. Then we have 1, 0, 0. So 1, 0, 0 is, this is 1 and 0, 0 is 4. So 4 is going to be 1. 4 is going to be 1. Then we have 0, 1, 1. What is the value of that? 0. So 0, 1, 1 is 0, 1, 1 is 3. So that value is also going to be 0. Now, next is 0, 0, 1. 0, 0, 1 is 1 itself and the value is 1. And 1, 0, 1. 1, 0, 1 is 5. That value is also 1. So, by looking at this table like this, we address 6 combinations. We address 6 combinations. But 2 are remaining. So, which are they? So, let us try to see that. Now, what I am doing is, I am just ticking which are the ones which are not addressed when I do this. So, you can see here, first one is 0, 0, 0. 0, 0, 0 is 0. So, this is addressed. 0, 1, 0. So, even 2 is addressed. Then 1, 0, 0. 1, 0, 0 means 4 is addressed. 0, 1, 1. 0, 1, 1 is 3. So 3 is also addressed. 0, 0, 1. 1 is addressed. And 1, 0, 1. 5 is addressed. So the ones which are not addressed is 7 and 6. 7 and 6 are not a part of these input combinations. So we will take them as don't cares. We will take them as don't cares. And that is how I have filled this particular excitation table, K-map. So you can see 1, 4 and 5 positions are 1, 1 and 7 and 6 positions are don't care. Why 7 and 6 are don't cares? Because they are not a part of the inputs itself. So probably we don't know what to do. So we just don't care about it. So we write it, okay, whatever may be their value, it's fine. Yes. Any doubts in how this K-map is filled? Please unmute and ask. So it is very simple actually. That is D is a function of S, R and Qn. But those don't care wherever you see X and X, there are two conditions there. So in all, if there are four and if there are two don't cares, we get six. And there are, so if there are six with with three variables, we get actually eight combinations, but there are only six inputs. So we identify which one of them are not a part of this input, and then we just put a don't care in that place. In this case, 7 and 6 are not a part, so we put don't care there. And others, we saw what was the value of D, and you can see that in 1, 4 and 5, D is 1. In all other places, 0, 3 and 2, D is 0. 7 and 6 are don't care. Now we can use K-map. So this will give me S, and this will give me R bar Qn. This will give me R bar Qn or Qn R bar. So D is equal to S plus R bar Qn. So D is equal to S plus R bar Qn. So what I will suggest is you can write only this thing, this K-map. No need to write the first one. Okay, Hemant has given the answer S plus R bar Qn, correct? Even Gaurav is right, S plus R bar Qn. Okay, so answer is okay, but the important thing here is how to fill the K-map from the above table. Is that point very clear to all? Is that point very clear to all? If yes, please say yes in the chat box. I want, because this is a sure shot question in the exam, so I don't want anybody to lose these simple marks. There are just one or two steps that you have to do and then you are done. That's it.
Sir,
Yes.
so can you please explain that K-map again?
Yeah. So I'll do that. 1 minute. Now you can see here. So you have understood how to make this table. SR flip-flop using D means SR will come here and D will come here, and transition states are common to both because both are in terms. What we have written for SR is the excitation table, and what we have written for D is also an excitation table in terms of Qn and Qn plus 1. Now we want to write D in terms of SR and Qn. So for SR and Qn, we are having these combinations 0x0. But how should I read 0x0? So I should read 0x0 as 000 input gives me 0 output, and 010 input also gives me 0 output. There are two conditions wherever there is a don't care. Then we have 100, that is a single output, 011 again single output. But now here we have x01. So how to read x01? We can read it as 001 or 101, and we can have 1 in two places for 001 and 101. So now you can see that these inputs S, R and Q and given ones cover only 6 combinations. So this covers 2, this cover 1, this cover 1 and this covers 2. So in all there are 6. That means 2 are not there. So the 2 which are not there, that is 7 and 6, we put it as don't care. Others we put whatever is given as per this excitation table of the D flip flop. Is it clear, Vishwas?
Yes, sir. And why did we selected that 1, 4, and 5?
1, 4, and 5. Okay, so this is 4. 100 is 4, and here we have two combinations. 001 is 1 and 101 is 5. So you can see for 4, 1 and 5, my D is 1. Did you understand this, Vishwas?
Yes, sir. But why didn't we selected that 011, third one?
011 we have selected na, but the value is 0 na.
अच्छा, okay,
0,
हाँ, 1 जहाँ आएगा.
here we are having
Okay,
zeros.
4.
So zeros
Okay.
we generally don't write na in that KMAP. We write only
हाँ.
1 and don't
Okay,
care.
हाँ. हाँ, yes, sir. Okay, sir. Clear.
So if you want, you can write 0, no problem, just for your own sake. But when you combine, you will combine only once and don't care, right? Did you understand, Vishwas? Please ask doubts. See,
Yes,
such
sir.
doubts are very important.
Yes, sir. Clear.
Okay, so
Thank you, sir.
now let us go to the actual implementation of this particular. So we can. So now we got a equation. D is equal to S plus R bar Qn. Now how to implement this? We are implementing SR flip flop using D. So at the input of D, I have to connect S and R like this. S plus R bar Qn. So this is the equation that I should keep in mind. D is equal to S plus R bar Qn. So I am implementing SR flip flop using D. So I have a D flip flop. I have a D flip flop which is having a clock and everything. But D is what? S plus R bar Qn. So here I'll get R bar. Here I'm getting S. From here what is coming is Qn. So here I will get R bar Qn, and this is a OR gate. So what will I get here? S plus R bar. So D is equal to S plus R bar Q. So actually as a black box, if you see, you are giving R and S, but inside there is a D flip flop. And this NOT gate, AND gate, and OR gate is the hardware that you designed so that this D flip flop could be used as a SR flip flop. This D flip flop could be used as a SR flip flop. Please draw this diagram. So this is the final implementation of SR flip flop using D flip flop. SR flip flop using D flip flop. Anusha and Shubham, did you understand when I explained it to Vishwas, or do you want
Yes, sir.
me to explain again? Anusha and Shubham, do you want me to explain it again, third time?
No, sir, I understood.
Okay, what we will do is we are going to do many such implementations. So we will do 3, 4, and in that flow you will have a even better understanding. So if you have completed this diagram, just write done in the chat box. Yes, somebody said something. I could not understand what you said. Sorry. Who's this? Yes. Soham, your microphone is not on mute. Okay. So if you are done copying this, then we can go ahead. Just put done in your chat box. I'll wait for another 1 or 2 minutes if required. Okay. Should I go ahead, Karthik, Anushka? Okay. So let's go ahead with the next one. So we'll see many. So that will give you the hang of this thing. So let's do now SR flip flop using JK flip flop. SR flip flop using JK. So you can see that SR, QN and QN plus 1 entries are the same. They have not changed at all. Only instead of D, now I have written J and K. I have written J and K. So this is going to be my input. So I have to write J as a function of Qn, S and R. And now also I have to write K as a function of Qn, S and R. So basically I have to solve two K maps. I have to solve two K maps. Two K maps. There are three variables. So 8 cell K map, and the functions will be in terms of Qn, S and R. So now I am going to design a SR flip flop using a JK flip flop. So please write this table with the exception of instead of D, now we are writing just J and K. And please note from the excitation table of J and K, we were having 0, 1, XX and XX, 1, 0. Okay, so if you are done with this table, just write done in the chat box. You can skip that what I have written at the top. Imports, flip-flop to be designed, all that thing you can design. You can just skip it. You can just write SR, QN plus 1, J and K. That's it. And start creating the K map for J. Start creating the K map for K. Okay, Gaurav. Just take some shortcuts. SR, QN plus 1, J and K. That's it. Don't write transition states, input flip flop to be used. ये सब मत लिखो. Don't write all this. Okay, so let's go to the. Should we go to the next slide,
Sir, please wait.
Karthik, or we'll wait?
No. Yes, sir, please wait.
Yeah. So once you are done,
I
just
don't know how I don't know how they are able to complete so fast.
सर वो मतलब एक
yes,
एक
that's what I'm
लिख
saying. Just right. Yes,
लिख
Gaurav,
दे रहे हैं लेकिन फिर भी
can you tell the secret to Vishwas how you are able to do it?
यस सर।
What, sir?
सर राइटिंग के लिए
Yes.
टाइम नहीं लग रहा है और अंडरस्टैंड कैसे करें फिर।
हाँ सर
Sorry.
ये सर मतलब जैसे ही समझने जाते हैं तब फिर हम लोग लिखते हैं।
हाँ
फिर
हाँ.
जब आप कुछ बोलते हो तो समझने जाते हैं। फिर कुछ लोगों का हो जाता है, डन कर देते हैं। फिर लिखना भी नहीं होता, समझना भी आधा होता है। सो
Okay.
इसलिए
So we will now onwards wait for a standard amount of time. Like once we do something, I'll wait for 3 4 minutes as a default. Okay.
यस सर, थैंक यू।
Yeah,
थैंक यू
we
सर।
will do that. So please tell me such things so that I will adapt to it. Okay. There is absolutely no problem. But still, I will suggest
सर,
that
टू द लेफ्ट।
you. But still, I will suggest that don't worry much about the writing part. Worry only about the understanding part. Because since the entire lecture is on record, you can always go back and understand at your own speed. But please stop me if there is a understanding problem. Okay. Yes, Vishwas, you can go ahead. Vishwas, you were
नो
saying
सर,
something?
आई वाज जस्ट कंफर्मिंग दैट। हाँ, यस सर। टू द लेफ्ट इज द क्या एक्साइटेशन टेबल ऑफ एसआर एंड टू द राइट इज द एक्साइटेशन ऑफ जेके, राइट?
Yes.
दैट इनपुट्स टू बी डिजाइन। हाँ, यस सर।
So now
ओके,
based
तो
on this,
बेसिक आइडिया वही रहता है।
huh, okay. So should we go ahead? Okay, so this copying this should not take now more time. So let's go to the next one, that is the K-map. K-map simplification for input J. So here J is 0 and 1 in two places, and otherwise it is don't care. So for so the first input is going to be, so this can be 0 or 1, and this can also be 0 or 1. So let's try to fill this. 0 0 0 is 0, so 0 0 0 is 0. Then next is 0 1 0. 0 1 0 is also 0, so here we have a 0. Then next is 1 0 0, that is 1. So there is 1 0 0, this 4 is 1. Then we have 0 1 1. 0 1 1 is 3, and that is don't care. So the output is don't care. And then we have 0 0 1, the output is don't care. 0 0 1, the output is don't care. 0 0 1 is 1, the output is don't care. And then 1 0 1, again the output is don't care. 1 0 1 is 5, again the output is don't care. And you can see again 7 and 6 are not addressed, so by default they also become don't care. 7 and 6 are not addressed, so by default they also become don't care. So now your K-map looks like this. So you have 4, which is 1, and then you have 5 don't cares at 1 3 5 7 and 6. So you have this don't care, and now you can very well see that there is a one quad possible, and you can simply write that quad as S, and J is going to be equal to S. J is going to be equal to S. So I told you that we don't have a SR flip-flop implementation. We in the lab yesterday also we did not do SR flip-flop using preset and clear. The reason for that is because J is equal to S, and when we do the simplification for K, you will see that K is equal to R. So basically JK flip-flop only behaves like a SR flip-flop. So you need not do any addition of hardware to implement the SR using JK. JK flip-flop is equal to SR flip-flop. But we need to prove that mathematically using K-map. So that's what we are doing. So if you have copied this particular K-map, then let's go to the next K-map for the implementation of K. So again, you will copy only one K-map. That's it. The table and everything else are the same. So we looked at input J now. We looked at input J. So similarly, now we will look at input K. So I will complete K. Then if you want, I'll come back to J again. So now let's look at K. So again, we will write here 0, 1, and this X is 0, 1. So again 0, 0, 0, K is don't care. 0, 0, 0, K is don't care. 0, 1, 0, again then 1, 0, 0, again K is don't care. Where is 1, 0, 0? 1, 0, 0 is 4, so K is don't care. Then we have 0, 1, 1, that is 1. 0, 1, 1 is 3, that is 1. And then we have 0, 0, 1, that is 1 itself, and that is 0. And then we have 101, that is 5, that is also 0. So you can see that you are having 7 and 6 again not there, so they will be don't cares. So your K map would look in this way, and obviously you can see that you can have a quad now, which will be having this 1xx, and basically this is going to be just r. So your K is r. So what did we see? J is equal to S and K is equal to R. So if J is equal to S and K equal to R, that means SR flip flop is the same as JK flip flop. SR flip flop is the same as JK flip flop. So in the Viva also they may ask you, can you implement a SR flip flop using a JK flip flop? So you should know conceptually that SR and JK is one and the same. So all you need to say is if SR and JK is the same. If you start solving it, that means you don't know. Are you understanding? Though you can solve, but it means that you don't know. So that is how the Viva will be there. So we need to prepare for that. So do you want me to go back to K map of J, or is it okay if we are on K map of K itself? Yes, Karthik, can you give me a voice check? Can you hear me? Shubham or probably Vishwas, can you give me a voice check, please?
Yes, sir, you are audible.
Okay, because
Yes, sir.
suddenly everybody is silent. So, okay. So just write the K map for this. So I hope now you are getting how to read this above table to calculate J and K. So previously there was just one input, only D flip flop has got just one input, but now we have JK. So the implementation will be very simple for this flip flop. That is, it is going to be just JK flip flop you have to show, and at the input you will just write S and R. That's it. So if you are done with the K map, just write done in the chat box. Okay, Atharva. Atharva, go ahead with the realization. Go ahead with the realization of the flip flop, which is going to be very simple. So it is going to be like this. Just JK flip flop with S and R as the input. So you will just write JK, just show a box, write JK, and at the input you can just write SNR because J is equal to S and K is equal to R. That's it. Now you all will do SR flip flop using T flip flop. You all will do SR flip flop using T flip flop. Come on. Those who have completed this, start the next one. SR flip flop using T flip flop. Okay. Okay. So let's go ahead. Realization of SR using T. So here we have SR. So SR will come here, T will come here. Transition states in between. So again, this is going to be the input and T will be the output and T has to be a function of S, R and Qn. So very simple, you have to solve only one K map and that will be a 8 cell K map. Why 8 cell? Because there are 3 variables and 2 raised to 3 is 8. Come on, solve this and tell me. So solve the K map and tell me. So I will ask anybody now randomly to unmute and tell me which terms are 1, which terms are zeros and so on. So you have to tell me. I will ask you whether 0 position is 1, 0 or don't care. So you have to answer that way. Okay, who will unmute and tell me this?
Hello, sir.
Yes, Hemant.
हाँ सर
Yes.
100 1
Uh,
A
not one.
4
You tell me.
4 1
No, no. You start with 000.
हाँ 0 0 0
Zero is 0. Then 001 is
0 1 0 is 0
010 is 0. Okay.
1001 sorry हाँ 1001
100 is 1.
and 0 1 1 is 1
011 is 1. Then
Then 001 is 0
Okay,
and 101 is 0.
0. And 7 and 6 are don't care.
I don't care.
7 and 6 are don't care. Okay, let's check this A map. That is perfect, Hemant. So here we are having 1, and here also we are having a 1. Here we are having don't care. That is right. Correct. So tell me the equation for T, Hemant.
Sir, uh, R given plus
RQN plus, correct. Go on.
uh, S given bar.
RQN plus RQN plus SQN bar.
Ah,
So these are your two pairs. Are these pairs the same, Hemant? Are your pairs and my pairs the same?
yes, sir.
Okay. So this is QNR and this is going to be SQN bar. So the equation becomes T is equal to QNR plus SQN bar. Correct. Okay. Hemant, what is your roll number? Can you just tell me that?
19103 B 0024.
Okay. ठीक है. Yes, everybody, have you understood this? Okay, let me just tell it to you quickly. This is 01. This is also 01. So 000 is 0. 010 is also 0. Then we have 100 is 1. Then 011 is 0. And then 001 is 1. As well as 101 is also 1. So the first two covers the positions 0 and 2. The second one covers the position 4. Then this is 3 and this is 1 and 5. So you can see that 7 and 6 have to be don't care. Okay. Vishwas, have you got a more clear understanding now?
Sir, in the third row,
Yeah.
the 011,
Hmm.
it is 3. So it should be 0, na?
011 should be.
हाँ, T में 0 है उसका. So it
No,
should be
no,
0,
no,
na?
no, no, no. So I have written it wrongly. This is 0 and this is 1. Sorry. Hemant is right. I made a error while I copied it.
हाँ, 0110 XOR, हाँ.
So just make that change. I'll correct it right away. Then you should have this. Does that solve the doubt, Vishwas?
हाँ, yes, sir.
because I think I copied the last column of the D flip flop, and for the D flip flop it is 0 1 0 1. So I changed it, but it did not reflect in the second table. Okay. So now let's go to the implementation of this flip flop. So that is going to be a T flip flop, and this is how it will look in terms of S and R. So here we have R, S, here we have Qn bar, here we have Qn. This is R dot Qn, that is my first term, and here we have S dot Qn bar, and here we have R dot Qn plus S dot Qn bar. This is dot, this is plus. This is my T. So inside we are having a T flip flop, but the inputs that we are giving is of SR. Please copy this diagram. So once you have copied this diagram, just write done in the chat box. So like this, 12 combinations are possible, okay? 12 combinations between SR and T. So you can also have here, this is SR flip flop using T flip flop. So you could also have T flip flop using SR flip flop. That's also quite possible. So I have listed down all the 12 implementations for you, but we will not do all 12. We will do two more to bring in the clarity of the concept. Okay, Shubham and Atharva have given the answer. Correct, Shubham and Atharva? So next is D using SR. Next is D flip flop using SR flip flop. Those who have finished the first one, start implementing D flip flop using SR flip flop. D flip flop using SR flip flop. So if you look at this thing as a black box, uh, here we are having this flip flop will have output as Qn bar, and if I put it in one black box, we can say that This is a SR flip flop, but actually inside we have some hardware plus T flip flop. So that is what we mean by implementation of SR using T flip flop. So what you are actually doing during realization is you are designing the hardware. Okay. So Karthik, your CR and DCR were on inverters. I have received a message from Karthik that due to heavy rains, he has finished off his battery and inverter and everything. So no problem, we'll consider all these things. But in case of any problem, just see to it that you go through the lecture recording at a convenient time of yours so that you are always in sync with the next class. Okay, so let's go to the next implementation, that is realization of D flip-flop using SR. Now you can again see that D is here and SR is here. So now you can see that there are just two inputs. S is in terms of D and Qn, and R is also in terms of D and Qn. So we can just clearly write here that S is a function of D and Qn, and R is a function of again D and Qn. That means we have to for solve two variable K map with four cells, and that we have to do twice, once for S and once for R. So we will have a K map for S, we will have a K map for R. So transition table is there for your reference. Start solving for S and start solving for R. So tell me what is S and what is R. Come on, do it quickly. Okay, B using SR. Yes, has given the answer. Okay, choose B, and R is beta. Okay, that is correct. Hemant also, the answer is right. Sachit also. Sanchit also. Sanchit, what about R? Sanchit Deshpande, what about R? S is okay. What about R?
सर डी बार एक्चुअली एंटर दब गया गलती से नीचे लिखा है
Acha, acha, okay. Maybe the chat is not loaded in. Okay, fine. So that answer is right. No problem. Yes, Parth will solve this for us. Parth Thakur, is he there? Is Parth there? I think Parth is not there. Okay, so let's see the K map. So here this is pretty simple. Here we have 0 0 and there are no don't care conditions also. So it's easier to see. 0 0 S is 0. Then 1 0 S is 1. 0 1 S is again 0. And 1 1 S is don't care. Fine. So we get this. Then obviously we'll get a pair here. And that is B. That is absolutely correct. So S is equal to D. And similarly, you can do it for R. So in the first case, you'll get R, then I think you'll get 1. Come on, do it. And the K-map simplification for R would be just this. So let's look at it for R. 0 0 is don't care. 1 0 is 0. 0 1 is 1. 1 1 is 0. Yeah, so you get this way, and that is going to be D bar. So R is equal to D bar. So correct. So just that pair appears at the top. Previously it was below, and that is why that D became D bar. So that's what isn't that what we have done. So we used to take a SR flip flop, S and R, and we used to put a NOT gate, right? And if you want to implement D flip flop, so that is what the equation says that here we want D bar and here we want D as it is. So that's what we verified just now. This is how we used to implement the D flip flop. Okay, so if you are done with this, just tell me the K-map is done. So we can go to the next implementation. Okay, Parth, something is wrong with your mic. And the answer is right. Yuan Sumant and Gaurav. That is correct. So the implementation of this would be this way, right? Like what we have seen when we did the D flip flop. So it addresses just 0 or 1. So either this can be 0 1 or it can be 1 0. So set or reset, if you can recall that. Okay, so now you start implementing D flip flop using JK flip flop. Come on, do D using JK. So what I want you to do for this week is that in yesterday's lab we have generated the symbols of D, SR, JK and T. So you can also generate the symbol for SR also, no problem. And you have already designed the hardwares. So what you can do is you can design the hardware, implement the flip flops using another flip flop in DSCH and check for yourself whether you are getting the same implementation or not. So that will be a very good practice for you uh, to realize one flip flop using another flip flop. But I hope you are getting the hang of how to design. Okay, let's go to the next one. So this you will design end to end on your own. Realization of D flip flop using JK flip flop. Okay, so I will ask some questions now. J is a function of what? Can you tell me J is a function of what?
S.
J is a function of which of the inputs in the above table?
DQN.
D and QN.
Sorry, J is a function of what? I could not hear that. Who is answering?
D, Q,
D
N.
and QN.
D and Qn. That is right. And K is a function of what?
D and QN.
D and QN plus 1.
No, wrong. It is just D and Qn again. That is why I wanted to ask. So see, J is a function of J is a function of D and Qn. And K is also a function of D and Qn. We have never been using Kn plus 1 at all. When we are doing the realization of one flip flop into using another flip flop, we are not using Kn plus 1 at all. We are just working with the excitation table inputs and the output. So J is a function of D and Qn. K is also a function of D and Qn. So that is what we are trying to do now. So Next question is, how many variable K-map will you use? How many
four
variable
cell,
K-map? 4-cell K-map. That is right. For both, we will go for 4-cell K-map. So we will solve one K-map for J, one K-map for K. So to be designed will always come here. Using that will always come here. Okay, so solve for J and K and let me know. Okay, J is D and K is D bar. Okay, correct. Anusha and Omkar and Hemant, correct. So let us see that. So transition tables are at the top only, no change in that. So here we have 0 0 is 0, then 1 0 is 1, then we have 0 1 as x and x. So don't care, don't care. So what we will have here is again the same thing, D. That is J will be equal to. So two variable K maps are really simple. So what does it mean? So implementing a D flip flop using any other flip flop, the implementations are quite simple. But if you want to implement the JK flip flop using a D flip flop, the implementation can be little bit difficult. So please note D flip flop has got just one input. So implementing a one input flip flop using a two input flip flop is pretty simple. But implementing a two input flip flop using a single input flip flop, so you will require quite a lot of hardware in between. So let's see the implementation for K. So K is 0 1 and 1 0 is don't care. 0 0 and 1 0 is don't care. 0 1 is 1 and 1 1 is 0. So you will get this as your K map, and you can see there is one pair. Quad is not possible. So this is the pair. This is B bar, and K is equal to B bar. K is equal to B bar. So this flip flop will pretty much look the same as SR. So we saw that SR was equal to JK. So if D flip flop was to be implemented using SR using a NOT gate, so it would look the same when you are implementing it using JK also. So here you have JK, Q, Q bar, and here also we will have a NOT gate. This is D, this is D, and here you will get D bar. As simple as that. Okay, so Shubham, Atharva, and Suman have done D flip flop using T flip flop. D flip flop using T flip flop. So that is the right. Shubham, you are right. Atharva is also right. Suman is also right. Good. So you should have this space. Very good. So you can take some shortcuts. No need to write everything, but yes, you should know how to solve. That is good. So good. You are ready with at least the first six. So it is 12:57. So it's almost 1 o'clock. So I think we'll end our session here. And if there are questions, if any, then I am here for another 5-10 minutes. Let me take the attendance.
के गीत का नाम
Yes, Amit.
सॉरी सर बाय मिस्टेक
Okay. Okay. Today I have received many emails from students saying that they have electricity issues and internet issues at home. I can understand that. So no need to worry. Just see to it that you have attended this lecture in the form of the videos, and I think that will be enough for understanding. We have gone slow through today, so slow means the understanding becomes better. Okay, so I have downloaded the attendance. So those who have completed are free to log off, or else I'm here for some kind of discussion.